Hello there, and welcome to another review of the Leetcode contest. So I managed to finish all 4 questions, so let's get right to it. First question, make the string great again. I mean just great, not great again. It was almost great again. So the point of this question is when you have 2 letters of the same type, so E and E here, but of different casing, you want to delete them. So the best way to keep track of this is to start from the end, because when we start from the end, if we decide to remove any letters, it's easier to keep iterating because removing letters remove the length from our string. So if we were to start from the beginning of the string, we would need to go back an index, and it would make things a little bit more complicated. So instead, I just started from the last index, and then while our I isn't at the start of the string, we check if we are within the bounds of the string, because when we remove characters, we can be outside. And we check if the conditions are respected. So if they are the same character, so we just lower both characters and check if they're the same, and check if their casing is not the same. So we can check if the first character is lower and check if it's not equal to the result of the second character that is lower. And to remove that part of the string, if it respects the condition explained by the problem, we just do 2 slicing. So S up to the point of I minus 1 and S after the point where we deleted. And then we go downwards. So the time complexity is O of n squared because we're slicing at each step, so that takes n in the worst case, and then we iterate over all the string, right? Yeah. So since the length was only 100, it didn't really matter. Next, find the kth bit in the nth binary string. So we had some recurrence relation. One thing that was interesting to notice about this recurrence relation is that the beginning of this recurrence relation never changed. And what I mean by that is SI, the first part of it is always SI minus 1. So we can always build on top of the previous result. So we could easily generate the nth element in the sequence by just appending what we already had, but iterating backwards because there was the reverse here, and just inverting everything we had. So that's what I do here. I just keep generating the numbers until we reach the length of k. So we append the 1, which is the one here, and then we iterate backwards on the sequence or the element, and then we XOR by 1 to flip the bits. And then when the sequence is long enough, we just return the kth minus 1th bit because it was 1 indexed. So that's it for this problem. Now, this was a really interesting problem because the way I managed to solve it is to reduce this to an interval problem, because when I see the term overlapping or non-overlapping, since there's so many problems with intervals based on the notion that you want to merge overlapping intervals or such, I wanted to reduce this problem to an interval problem. So my goal was to create intervals, and the numbers within that interval, if you sum them, it would give you the target. And then there's a known algorithm to return the maximum number of non-overlapping intervals, which I think is the class scheduling algorithm. If we do a Google search for this class scheduling algorithm, I don't see it right here, but basically we can sort by the end index and pick the intervals that end the soonest greedily, and we always get an optimum result. I'm not sure of the proof of this, but it works. So here's how we do to get the intervals. So first we can generate a prefix sum array doing this, and then we iterate over every term in our prefix sum array, and then we find the complement in regards to the target we have. So we take the current prefix sum starting from the start of the array. And then we know that if we reduce the number that is the complement from target, we will get our target. So what I mean, if we do n minus comp here, we will get target. So basically it's like the inverse in regards to target here. So we check if we found target in the prefix sums, and if so, we can add an interval from the index we've seen, that last number, and the current number. And then we set the scene of the current value to the current index, like that. So that's another technique that is not well known, but it's known for finding subarrays with a certain target. So then we apply our second algorithm to maximize the number of non-overlapping intervals by sorting by the end value here. And then we iterate over every interval if we can pick it. So if the start of the current interval is greater than the last one we picked, we increment our answer and we set the last to the current ending. And that should do it. So for the last problem, very interesting dynamic programming problem that I had some issue with, because I was trying to make it work without modifying the original input. But if you add a 0 and an n, in this case a 6, it really simplifies how you deal with your bounds. So my solution was this. First we sort, so we can just iterate over it linearly. I'm not sure if it really matters though. Yeah, it probably does. Because you want every cut that is between certain bound to be in between. Yeah, okay, it matters. Then we insert 0 at the start and at the end. And then the recurrence relation is as follows. We basically track the index of the current cut. So we want to start with the cut 0 and the last one here, which aren't really cuts, but we need those values to be able to compute the cost of cutting for the current subproblem. So we know that if each cut is next to each other, there is no cut in between them. So there's no more cuts to be made. So the answer is 0 in that case. Otherwise, we iterate between every cut in between the current cuts. So at the start we have 0 and 7 as the edges. So we iterate over 1, 3, 4, 5. And then we try creating subproblems with 0 and 1 and 3 to 7 like this. So each time we have 2 subproblems, and we try to minimize the results of the subproblem. So the subproblem is from I to k plus k to j, and then the cost is the cuts of j minus the cuts of I here. So the cuts of j is the end of the current cut minus the start, so we get the length of the current subproblem. So that's the cost here of the length of the stick to be cut. And then the new length of the new sticks is the left part starting from the until the cut, and the right part starting from the cut right here. And we just memorize this and it's good enough and it works. Crazy, right? It amazes me each time how we can solve complex problems like this with dynamic programming. Thank you for watching and see you next time. Bye bye.